Hi, this is Arpan, and today I will discuss about GAN, which is Generative Adversarial Networks, and I will be discussing about how to implement GAN using the TensorFlow. And with the help of this, you can generate any kind of new data. In this case, I am taking a image data, so you can generate new images like this. So it is all these images are created from the noise once the network has learned how to generate a new images in this case. So generator adversarial networks can be used for generating new kind of data. So in short, maybe I can just give you a glimpse of what GAN is in this case. So you see there are two neural networks which are working together. So one is called generator and the other is called discriminator. So generator is actually taking random noise as an input, and it tries to create an fake image which should look alike with a real training data set. And what discriminator does is it takes the sometimes it takes the image from the training set, and sometimes it takes the image from the image which is created by the generator, and it tries to discriminate whether the image is real or fake. So if the image is coming from training set, the discriminator will say it is real, and if it is coming from generator, it will say it is fake. But the thing is, the generator tries to make as real as possible. So sometimes the discriminator may be fooled by saying that this fake image is a real one. And maybe sometimes discriminator is not able to discriminate between real and the fake. And sometimes it may say that the training set image is a fake image. So main objective of training these two neural networks, which is generator and discriminator, is to optimize for their learning power. So discriminator should be good enough to discriminate between a real and a fake image, and the generator should be good in creating a new image from the noise which should look alike with the training data set. So you should keep in mind that in the generator, the input dimension is the number of rows, which is the number of observations, and the columns will be the random noise dimensions, and the output will be the dimension of the image. Whereas in the case of discriminator, you see the input is the image dimension, and the output will tell whether it is real or fake, which is a 0 1 probabilities. So it will be one dimensional, it is saying 0 or 1. So I hope you understand this. This is a very short description of how this will work. So let's see. So let's first import the libraries, import all these libraries, and this TensorFlow.examples tutorials MNIST. Import the input data, and which is we are using for importing the MNIST data set. So if you do the second line of code, it will load the MNIST dataset. You have to write one hot is equal to true so that the labels are one hot encoded. So now we have the data inside the df object. Now we are providing the neural network parameters, which is the image dimension. So image dimension will be this this image dimension is 28 by 28, which will be 784. Generator dimension, which is like inside there will be one layer which will have the dimension of 256. We can change it as we want. And then we have discriminator dimension, that is again the internal layer inside the discriminator, which is again 256. And then the noise dimension, which is the dimension of here. So noise dimension will be given as the number of rows, which is number of observations, and the number of columns will be the noise dimension. The noise dimension is 100 in case. So you can say that it is a two-dimensional matrix which is fed into the generator, with the rows being the number of observations and the column being the noise dimension. Once it is being fed, it is converted into the dimension of generator dimension internally, and then it is finally converted into the dimension of the image dimension. And then this image dimension is fed into this discriminator, and the dimension of that image is then converted into the discriminator dimension, and then later on it just converted into the sigmoid probabilities, which is 0 and 1. So what we are doing is, after this first one we will use the railway activation, at the last we will use the sigmoid. So we will discuss about that later. Let's first input the data. So generator input we would require here, and then discriminator input is which is here. It is a two-dimensional matrix we can see, and in the generator the input dimension is we don't know the batch size initially, so what we are just writing is the row dimension as none, and the column dimension will be noise dimension, which is given here. And for the discriminator dimension we know that it will be image dimension. Image dimension we are saying because image dimension is not 28 by 28, it will be 28 by 28, which is 784. So image is squeezed in the form of straight, so you can say straight line. It is not two-dimensional. No, it is a vector format. So it is 28 by 28 when you squeeze it, and it makes 28 by 28 a straight line vector. So it is 784. So you are feeding it into 784 columns, and the number of rows will be number of observations in the batches. So that is again the none. So now we have given the generator input and the discriminator input. We have encoded as placeholders, TensorFlow placeholder, tf.placeholder, and encoded as at float 32, tf.float32, and the shape is this. Now we are giving the neural network training parameters, which you can change. Of course, batch size we are taking as 128. Number of steps that is used during the session training, I will explain you later. And learning rate is actually the rate by which this algorithm will try to optimize the neural network training. Display step is also which is we are going to discuss while we are doing the training session. Now let's first define the weights initialization, which we will require, because we see here we are feeding the noise dimension. We will multiply with some weight matrices and add the biases, and then get some again two-dimensional matrix. Then again it will be matrix multiplication will be done with another weight matrix and added the biases, and then again the sigmoid. So something similar we are going to do. So we would require 4 weights and 4 biases, 2 weights for discriminator, 2 weights for generator, and 2 biases for discriminator and 2 biases for generator. So what we are using is we have written this weight function, and this is similar to tf.random normal. Only difference is that we are defining the standard deviation, and the standard deviation should be something of the shape which we are providing, and that should divide by the square root of it. So the weights which we are defining is the weight is W1, W2, W3, W4, and the initial first 2 weights is the these weights will be used in the generator. So first as we know that it is the noise dimension, which is the number of rows, which is none, and the number of columns, which is the noise dimension, and that will be multiplied with the W1. So noise dimension, generator dimension, and then generator dimension will be converted into image dimension. So you can see like this. So first we are feeding here we are feeding the matrix with none, noise dimension, which is generator input, none and noise dimension. That is then converted into noise dimension to generator dimension, and then generator dimension to image dimension. So something like this which is going to happen. Similarly, for the discriminator, what we are feeding in, we are feeding the images in the format of none and the image dimension, which is 784, 28 by 28, and that image dimension is multiplied with the W3, which is image dimension, and then it is converted discriminator dimension, which is the internal encoded format of 256, and then this discriminator dimension is converted into 1, which is 0 or 1, and we will be adding the biases B1, B2 to W1 and W2, and B3, B4 with W3 and W4. So let's write the generator function and the discriminator function once. So the generator function which we are going to write is like this. So we are inputting this x, which is this one, none and noise dimension. So none and noise dimension will be matrix multiplied with the W1, which is noise dimension and generator dimension. So we must be knowing that how the matrix multiplication happens. The number of columns should be equal to the number of rows. Only then there will be matrix multiplication. So we know the dimension of x, which is none and none noise dimension. None means the number of observations in the batches, which we don't know. So we can say none right now. So none noise dimension will be multiplied with W1, which is noise dimension, generator dimension. So none noise dimension times the noise dimension, generator dimension. So it will be converted into a matrix which will have the dimension of none, comma, generator dimension. Then this none, comma, generator dimension will be multiplied with W, which will then create a matrix multiplication, and it will create none generator dimension times generator dimension, image dimension. So it will create none, comma, image dimension matrix, which will in turn be fed into the discriminator. So I hope you know about the matrix multiplication, how that works. So that's what we are doing here. So tf.mathmul x is multiplied with W1. We are accessing the W1 weight of with W, and then we are adding the biases, which is B1 to H1, and then we are doing the ReLU activation of this layer so that we have non-linearities in this network. And again we are adding one more layer, which is again matrix multiplication with W2, and adding the bias and then sigmoid activation, so that we have the probabilities, and we return the H1 at last for the generator. Similarly, we create for the discriminator. We are feeding the x as the none, comma, image dimension, which will be converted into none, comma, image dimension multiplied with W3, which will be none, comma, image dimension times image dimension, comma, discriminator dimension, which will be equal to none, comma, discriminator dimension. Then none, comma, discriminator dimension will be multiplied with discriminator dimension, comma, 1, which will create none, comma, 1. So it will be, at last we will be having a one-dimensional vector, which is going to give you the probabilities for each of the observations and the batches. So that's what we have done. So x multiplied with W3, and then we had added the biases V3. We have done the ReLU activation, and then we have done the matrix multiplication with W4, added the biases, and then did the sigmoid activation. So this is all about the generator network architecture and the discriminator architecture. We can definitely change and by adding more layers or something like that. Now what we are going to discuss about how to optimize this cost function of these two networks. So we have the gen underscore fun as the generator function, disc underscore fun as the discriminator function, and now we are inputting the generator underscore function, gen underscore function. We are inputting the input gen underscore in, which is this one, and we will get the output, which is the generator output. This generator output will be fed into the discriminator function, which will give the discriminator fake out. And for the discriminator, we are also giving the discriminator input, which is discriminator real out. If we see here, for the discriminator, we are giving the images from two ways. One is from the training set, which are the real images, and one is from the generator, which is the fake image. The discriminator aim is to discriminate between two images, and it should be optimized in such a way that it can say that it is coming from real image or the fake image. So now we are creating two optimizer or optimization algorithm, which is Adam optimizer, similar to stochastic gradient descent. which is discriminate generator optim algorithm, which is we are feeding the learning rate. Learning rate is same for both of them. With first is generator and then the discriminator, and then we are optimizing the cost function. For the cost function, we have to optimize. We have to reduce the average for the outputs. So for the outputs of the generator, we have is gen out, so it has 0 and 1. We want to we have the probabilities. We want to increase the probability. If you see the disk fake out, if it is 1, that means generator is creating almost a same image, almost a real image. Then this disk underscore fake underscore out will be 1. In that case, tf.log of 1 will be 0. That means the cost is 0. In the other case, when the disk underscore fake underscore out is tending towards 0, then this will be log of 0 will be very high. So cost will be very high. So in the similar way, for the discriminator also, since we are feeding the two images, one is from the training and one is from the real image. For the real images, it will be like tf.log of disk real out. Again, if it is 1, then log of 1 will be 0. And the disk underscore fake underscore out, if it is 0, then it will be the tf.log of 1 minus 0 will be tf.log 1 minus 0 will be tf.log 1, and tf.log of 1 will be 0. So disk underscore fake underscore out has to be 0, because it is saying that it is the output of the discriminator, and discriminator should say 0 when it is coming from the fake. Otherwise, it should say real image is 1 and the fake image is 0. You should keep in mind. So now what we are going to do is we have done these two things, and now we will be writing this variables which we are using in the generator and the discriminator. And for the generator, we are using W1, W2, and for discriminator we are using W3, W4, and the biases B1, B2 for generator, and discriminator B3, B4. So this is a list of these weights matrices. And then we are writing a training optimization function, which is optim underscore gen dot minimize the cost function of generator, and the list of variables which are to be fed into for minimizing this cost function of the generator. And so, for the discriminator, it is to be minimizing the cost of discriminator, and the list of variables for minimizing this is vars underscore discriminator. Now, once we have done this cost function optimization and all this thing, we are going to now initialize the variables, start the session, and give the batches to the session, and see what is the accuracy and the cost function for the generator and the discriminator. So with tf.session as ses.run init, we are initializing all the variables. For step in range 1 to number of steps, so steps we have already defined there in the starting. We are taking the batch underscore h x. We don't need the batch underscore y in this case. The next batch size we have already given there. So we are taking from the training images. We are taking for each step we are taking a next batch, and then that is fed into that is stored in batch x. And we know that for the generator we need the noise, so we are creating the noise temperature noise variable, which is a random variable, two-dimensional matrix between -1 to 1, which is Gaussian, which is random uniform distribution, and -1 to 1 with the size of batch size, which is the number of rows, and the number of columns will be noise dimension, which I have already explained. This is what we require for the generator input, which is we are giving the dictionary. So gen underscore input, which is the gen underscore input is noise temp, which is the noise which we are feeding into the generator. And for the discriminator, we are feeding the images, which is the real images batch underscore x. So for the discriminator we are having this input, for the generator we have this input. So for the discriminator also there is an input which is coming from the generator, that is inbuilt. For the initially you have to give the discriminator the input which is coming from the training images. Now you are giving the sys.run training underscore gen, which is the training minimizing this cost function of generator, and training underscore disk is the minimizing the cost function for the discriminator which you are writing. So all this is the list of all these four objects which you are trying to calculate. So training underscore gen, training underscore disk, cost of generator and cost of discriminator, and you have fed the this dictionary which is required for calculating all these. First training underscore gen and training underscore disk is not required, but GLN and cost of generator and cost of discriminator is being required. So we will be printing at each of these steps. After each 2000 steps you will see that what is the generator cost coming and how it is reducing, and what is the discriminator. After many iterations, I have chosen 80,000 iterations, you will see that generator will learn about his task. What is his task is to create new images which looks like a real image, and the discriminator objective is to discriminate between the real and the fake image. So they both will learn as the time passes by. That means as the number of iterations goes higher and higher, so it will learn more and more. So for the testing purpose we have created a canvas, and we have something like this. So 1 2 3 4 5 6 6 by 6 we have here 36 images, and what we are doing is we are creating a random noise and then feeding into the generator network and feeding this generator input Z, which is random noise, and from this random noise it is actually calculating using G, which is the output of the generator, and we are then reshaping it here in the format of 28 by 28, and it shows all the images in this format. These all images are being created by the generator network. These are not real images. These are the images which are created by the generator network, which generator has learned how to generate new images from the noise. So this is the last part of the testing, and it shows that our generator has learned a lot. So I think this would be clear that how we can perform generator adversarial networks, and you can implement in TensorFlow. So thanks for watching this video. If you have liked this video, please do not forget to do like and subscribe, and if you have any confusion you can just comment, and you can also go to my GitHub account, and you can just have you can clone this repository, and this is Arpan G87, you can just see there. So thanks for watching this video. Bye bye.